Hi, let's start with problem 15. I didn't make the solution to problem 14 quite clear, though I think I went through all the details needed, so I'll just explain the situation we've got then. So the base field is FQ, and then we have the polynomial ring with, I think it was M indeterminate, and then an ideal of polynomials. So let's just do that. We have FQ to XM, and there we have an ideal generated by F1 to F something. I don't know, Fs. And then we have the projection to the residue ring, or the variety defined by the functions. Now we have a point in some extension. It's an algebraic point, so it's in some finite extension, and it's called D, or some D. So we have a point A1 to AM, satisfying these equations belonging to there. Then we have the extension field, FQ to D, and its polynomials. The first is that we have a maximal ideal in this field defining exactly that point. We call it capital M for maximal ideal. It contains of all the polynomials that vanish at the point P, which is easy to see, and the residue field is just evaluation of the polynomial at this point. So it's just FQ to the dth, so it's field, so this is a maximal ideal, which I proved directly in the previous video. Now it projects down here, and I claimed that the ideal here contained the minimal polynomials of the AIs. We call them GI of XI. And of course the minimal polynomials lie in this ideal. And we can't have many more, as far as I can see. But then the question is, when we go down to the projection here, where do we end down here? we end in an ideal by definition. And since this is a maximal ideal, I believe this is as well. That was the thing I started with saying in problem 14. I had a feeling we would be needing it, and this is where we need it. If there is a larger ideal here, then there's a larger ideal up here as well. That's about it. Now, I've read this several times just to understand what it's about. This point, where does it occur in the sum of the zeta function? So it occurs for every r where the point lies. So that's all extension fields. And they are exactly, this is trivial, they are given by how do we say it? We want f q to the dth to be a subfield of f q to the x. And what must x be? And that this is equivalent to d dividing x. So that means x must be powers of d. That's one of the things I learned about finite fields in the last section. So that is this point. Every time it's multiplum of d, we will have, and that is that we get 1 here only for multiply of d, and that means the contribution has the form x sigma n, and then this must be a multiplum of d. What do they use? kd divided by kd t to kdth. So we should of course compute this. And when I just read section 13 and done that, then I knew how to handle this. Oh yeah, it's a series of t to the dth in various powers. So it's t to the dth in k. And it contributed unity. And then 1 divided by k, we take out d. So this gives the logarithm of 1 minus t to the dth. So I get 1 minus t to the dth and a kth root. Now what does it say we should get? Well, well, well. I agree, it doesn't look at all like what we used to get. Oh, the sum is, of course, minus ln. So that gives the 1 divided by. Now, the maximal ideals m, then degree m, I think they mean the norm of m. They wrote what they meant by degree m somewhere. Norm m. Norm m is q to the degree of m. All right, that's new. Well, let's just accept that. And m is the maximal ideal here, yeah. So what did I make wrong here? Oh, we have to take the exchange those. So we get t to the dth, not t to q to the dth. Oh, that's not the norm. Oh my god. Oh, that's only down in the. I don't need to take notice of any of this. It's just the cultural note that we are probably going to do in the next section. So degree m (1 minus t), but where does this k go? D, and then it's d to I just copied this. It should be minus first. It's for each point, it's the product. But we have to think of the entire ideal. And how many points do we have up here? So they claim we have d points. Now, if we go up to the algebraic closure, which is the union of all of these fq to the dth, then we have all the solutions with this minimal polynomials, and I believe that's the product of the degrees of the various they are conjugate, and the conjugate of this is itself conjugate OFQ. It's the only so all solutions lie in here. And why must that be D solutions? Oh, it's because it's order D over Q, over FQ. This is not quite satisfactory, but I simply think that we have D points in this field conjugate of this. Maybe we can even find them by applying the Frobenius automorphism up here. It's a little weird though. My thinking here is if we have a simple circle, 2D, and then we take square root 2 and square root 2, and then when we use an automorphism up here, we get 2 points, square root 2, square root 2, and minus square root 2 point minus square root 2. We don't get all 4 combinations, but then we might have many combinations here which we don't get at all. All right, so that's what we need. And then this is obvious then. So problem. I didn't put double bars on here. All right, that was it for today. As you know, it's Tuesday, 27th September, and I'm going to my dance lesson in about an hour. So I just have to take my afternoon coffee and some apple pie. See you later. Hello. Today is September 29th. The first recording stopped with some questions like, given a maximal ideal of the function space, in which fields or extension fields of Q do the points occur, and how many are there when they occur? So that was the basic question. And then I make some examples to try to understand the phenomena that are going on. And I did this yesterday, but unfortunately there was no sound on the recording, so I'll just repeat it, not repeat what I said, but show what I did. First I looked at a circle, the unit circle over F3, which I've been using before. In F3 we have these 4 points, and the maximal ideals are given by this. Then when we go to F3 squared, we have I take the extension to be given by this minimal polynomial. It's not the usual one really. I think the usual one comes from factorizing x to the 8th plus, I don't know, never mind. This makes computations easy. And if we use this, then t squared is -1, which is equivalent to 2 modulo 3. So that means we have 4 solutions. And plus minus t has this minimal polynomial, and of course the same with y. So that's the maximal ideal, and it has norm 4, and the solutions already occur in F3 squared, so d being equal to 2. That was one example. And then we take the circle that its radius square root 1. In F3 we have the solutions plus minus 1 point plus minus 1. And again we have 4 maximal ideals, each of norm unity, each giving 1 solution. And when we extend to F9, I found 4 solutions. Did that long time ago. Don't know if you remember it or I've seen the video. And there were those. So the maximal ideals were these, each giving rise to 2 solutions and lying in and BD equal to 2. So the norm of these ideals is 2 and D equals 2. So that was what I made yesterday. The next thing is to generalize it and points on the curve. That is of course the norm of the ideal. Next, what is D? So that means in which extension field of Q that should be plural, do the points occur. And the first thing I realized was that all the points occur at once and continue to be there. I'm not sure I gave the argument there. But if this, that's a bad example of a polynomial, if this polynomial has solutions in fq to the dth, then it will split in it . not sure why that is, by the way. Well, now, the points was the norm, and that means that's the product of the degrees of the minimal polynomials. And the minimal polynomials, I think I called them, can't call them GJs. And the D, you see each, the solution to this guy comes in degree FG1, and the solution to this occurs in Q2, the degree of this polynomial. And then we need to find a field, an extension field, containing both of them, and that would be the least common multiply. And the point is here that D divides the norm. And now we should be able to compute the contributions from all the points given by a maximal ideal. So contribution, it's a factor, of course. Zeta t equals x of the sum, so number of points divided by, and it starts in D. So we have some Q, we are in FQ, and then in FQ to the dth, we start getting points. So it's KD, where K goes from ups, K goes from unity to infinity, times Tn dk. And the number of points, that was just the norm. And we can take D out as well. And it's 1 divided by K, T to Dth to Kth. Minus ln 1 minus t to dth and that should be raised to an m divided by d. Now that's my solution, and let's see what it says. I don't write the answer. Oh, there's the product over all maximal ideals of M. Yeah, so I should write the Z function and it should be degree of n. And what's the degree of n? Is that the norm? It should be. It should be the degree of the norm. So I don't get to minus first, I get to some higher power, and that's a phenomenon that occurs in this example. So we should make a product over all the ideals. So the total zeta function is a product of maximal ideals in the function ring T to D. That was what was D? It's the least common multiply of the degrees. We just write D. So norm of m divided by D. There we go. That was that. Then we have to show that it actually lies in one, so that is, we must expand it. Oops, this is a power. It's an integral power. And now it's obvious that when we expand this, first use the multinomial formula and then expand it, we will all get unity plus something with t and then integral coordinates. I believe that was what I needed to show. Yes. Oh, it's of course not a polynomial but an infinite series. There we go.